Yo, all right, here we go. Start of calculus. We're going to start with a limit motivation problem. Hopefully, it motivates us to want to learn limits. You guys can be the judge of that. All right, so here we go. It's a pretty neat problem. Kind of made it up. Tried to use as much relevant and accurate data as I could. So we have an Airbus A380. This plane right here. Picture doesn't do it justice. It's huge. Google it. You'll see that. Um, Actually, rode one of those guys going over to Bali. It's an awesome plane. Anyway, it's at the base of a runway. It's about to start accelerating down the runway so that it can take off. And we're going to assume that the plane has constant acceleration. That might not be entirely true, but we're going to, for the purpose of this problem, say that it does. So its acceleration is constant. And then we have the following. The linear position of the plane along the runway can be described by this function. X of t equals 0.5 t squared, where x is measured in meters, t is measured in seconds, and then I'm telling you that x of 0 equals 0. All right, so let's kind of maybe start to visualize this a little bit here. All right, so we got this runway, and there's going to be a plane here. There's my plane, and it's at the base of the runway, and this right here is going to be time 0. So the plane is starting from rest. And the position is going to be x equals 0. We'll say this is 0 meters, and then 1 meter, 2 meter, 3 meters, etc. as you go down the runway. And that's what this x of 0 equals 0 is telling us, all right? That at time 0, we're at 0 meters, all right? And so it typically, believe it or not, takes an Airbus A380 about 78 seconds before it takes off. So there's going to be this period of 78 seconds, which if you're actually in the airplane probably feels like forever. All right, so 78 seconds, the plane is somewhere over here. Let's say t equals 78. And depending on the weight of the plane and who's in the plane and how much cargo's on it, etc., the wind, all that good stuff, okay, the plane starts to take off. All right, so that's basically the setup of what we have. Now, what's this position here? I don't currently know this position, but I certainly can figure it out. And we're going to need to do that in a second. So the first question that we want to ask is, what's the average speed of the plane during this interval? All right, so over this interval, what is the actual average speed of the plane? So that is a pretty easy question. You don't need calculus to figure that out. All right, so most of you probably already know how to do it. So if I wanted to say average speed, or maybe even I'll call the speed here rate of change. So average rate of change, right? It's basically going to be the distance covered divided by the elapsed time. So the change in functional value that we're interested in here, which is the distance over the change in time, we'll say. Okay, so this is going to be change in distance. I did D, you can use any variable you want, and this is going to be change in time, which makes sense because if you think about it, say you go on a car trip, right, and you do 100 miles, and it took you 2 hours to do that. Everyone gets that, yeah, you average 50 miles per hour. So this is nothing new for you. So for average rate of change of functional value over change in independent variable value. So we're going to do this now. I need to get the change in distance, and I don't know what this distance is here. But I do have a function that I provided you that would give you that, right? This gives you that. So if I did x of 78, all right, so in other words, put 78 seconds into this, 0.5 times 78 squared, crunch the numbers, do the math, I'm going to get 3,042. All right, so remember that's meters. So 3,042 meters. That's about 3 kilometers. So that right there is a little bananas, right? It takes an Airbus about 3 kilometers to take off, and it does, which is insane. So now if we do this, if we do the change in distance, it's the final distance minus the initial, which was 0, right? Because that's 0 right here. And then over the change in time, 78 minus 0, and we just crunch the numbers here, pretty basic. If you do that, you're going to get 39. But what's kind of important, or what I want you to know is, well, what are the units here? Well, just think about the numerator here. These are meters, 3,042 meters minus 0 meters, right? So meters up top, and then this is seconds, so meters per second. So you get 39 meters per second. So that's kind of fast, right? I mean, think about it. You travel 39 meters in 1 second. That's fast. But now that's the average rate of change. If you want to give this some sort of meaning, you can convert this to miles per hour, and meaning for us, because here in America, we do a lot of things with miles per hour, right? And if you were to do that, and I'm not going to show the conversion, but if you were to do that, you get about 87 miles per hour. All right, so this thing averages 87 miles per hour as it goes down the runway. Now, that doesn't seem too fast for a 500-ton airplane to take off. But remember, that's the average speed. That's not really how fast it's going over here. So in calculus, we usually start off with things like averages, but then what we're really interested in is instantaneous values, values at moments, right? So what would be a better question to ask, and this was question 2, is, what if I wanted to find the instantaneous speed of the plane at the moment of takeoff, right? So at 78 seconds, if I was to look at, a snapshot, take a little picture of the plane as it's taking off. So right here in this little picture, how fast is it going at that instant? Okay, that is the better question. So how would we do that? So you might think, well, just use the same formula, right? I know it says average rate of change, but whatever, let's use the same formula. So think about for a second why you can't use the same formula, right? So if I'm trying to figure out now, and I'll update my picture, right? How fast is the plane going in this snapshot, right? At the snapshot that t equals 78 seconds. How can I do that? Well, if you try and use the average rate of change formula, there's an issue. And what is the issue? Well, what would the change in distance be at an instant, at a moment, at a snapshot? Right now, we're just looking at it at an instant, not over an interval. So what does that mean? Right? That means that there is no distance covered, right? So there is 0 distance covered. And there is 0 time elapsed because it's not an interval. So you would get 0 over 0. So the funny thing is in limit world, when we start to get into limits, this means something. This is actually called an indeterminate form. Indeterminate, as in you can't determine anything. But in regular math world, if there is such a thing, this is not defined. So basically, this tells us nothing. This doesn't, obviously there's speed here, right? It's going at a certain rate, but this clearly is not working. All right. So this formula fails. And that's because there's no distance covered and there's no elapsed time. So then the question is, all right, we don't have a magical formula for instantaneous speed, right? You can't just plug things in. So is there a way, and this is what calculus is all about, and I love it, is there a way to use this formula, right, where instead of trying to get the exact value, maybe we can estimate how fast the plane is going? So now remember, to use this formula, you need an interval, right? So the first interval we chose was from 0 to 78. And we got that the plane was doing like 87 miles per hour. And that really wasn't very accurate because it's definitely going a lot faster before it takes off. So you can have the choice of, well, pick a different interval. Pick a different interval that you think might be a better interval for estimating the exact speed, the instantaneous speed of the plane at this snapshot, at this moment. You can pause the video and you can think about that if you want. All right. Once you unpause, let's talk about it, right? Why don't we, and there's more than one right answer here, by the way, but I'm going to say, you know what? Why don't I look at the interval from t equals 78 to some slightly later time, right? Not drawing the scale here, to 78.01 seconds. All right, so we got the plane here, and we got the plane here, right? So we're going to look at it now over this tight interval. And I'm going to find the average speed over this interval. And I'm going to say that would be an estimate of the instantaneous speed at 78. All right. So let's see if this makes any sort of sense. So let's do it. All right. So here we go. So I'm still, writing average, I'll even write it out, rate of change, because that's the formula that I'm using. We just happen to be doing it now, and I'll write the interval out over the interval 78 to 78.01. Right? So now change in distance. I would need to know the distance here, right? So I already got the distance here, right? We did before, we did x of 78, and I think we got 3,042 meters. Well, now I'd have to do x of 78.01. So 0.5 times 78.01 squared, right? That's the formula that I gave you, right? Convenient enough. And if you do this, you get 3,042.78005 meters, okay? So not much further, right? Which makes sense because it's only 0.01 seconds later, right? So now if I do change in distance, I'm going to subtract these two values. So I'm going to do 3,042.78005 minus 3,042 point nothing, right? I don't know why I wrote that little decimal there. And then over the change in time, which is 78.01 at the later time to the earlier time, which is 78. Notice we made the interval different, okay? And when you crunch these numbers, and it's actually pretty easy, you could probably do it without a calculator because, I mean, let's think about it. 0.78005, that's an easy subtraction right here. And then 0.01, right? Just moving decimals here. You're going to get 78.005. Again, don't forget, this is meters, this is seconds, meters per second. Handwriting is atrocious right now. All right, so now again, you're like, well, what does that mean? Again, you can convert this to miles per hour just to kind of give yourself a general understanding of what's going on. If you do that with the proper conversions, I'm not going to take time to show that. You can ask Siri if you want, if you don't want to actually do it. But it's about 174 miles per hour, which actually makes a lot more sense, all right? That this plane is going to have to get, this 500-ton plane is going to have to get to around 170 miles per hour for it to actually take off and fly in the air. All right, so what we did here is we estimated, right? Because this is, remember, this is average rate of change. So if we tighten the interval up and we do average rate of change, we get an estimate, right, for the instantaneous rate of change. You can see it's been a while since I've been using this pen, all right, because my handwriting is pretty bad. All right, so here we go. So the question is, well, how do you make it better? Because if you're saying this is an estimate in calculus, I'm always interested in making my estimates better. So what if I want a more accurate estimate? What could we do? Again, this would be a good time for you to pause the video for a second and think about that. Think about answering that question. When you come back, hopefully you said make the interval smaller, right? So in other words, again, not to scale here, we just looked at, from 78 to 78.01. Well, what if we tighten the interval up and we go 78 to, again, not to scale, 78.001, or tighten the interval up again and go 78 to 78.0001, right? So you can keep making the interval smaller, right? As long as you have an interval, there's going to be a subtraction. You're not going to get 0 of 0. You're going to be able to use that average rate of change to estimate the instantaneous rate of change. So you're basically driving the length of the interval, right? So driving the length of the interval to 0, right? And you're like, oh, if you had pre-calculus last year and you were able to get into limits, which you may not have been, but if you were able to get into limits, then you would be like, yeah, this sounds like a limit, okay? And that's it, and that's the motivation. So that's actually like a pretty neat thing. You're able to find rates of change at a moment in time using this concept of a limit, all right? So the last question here is probably the most challenging, and you probably could skip it if you're just in Calc AB. But if you're in Calc BC, I would recommend that you don't skip it, which is how can I actually represent the instantaneous rate of change? So no more estimating, but actually represent the instantaneous rate of change. And we'll do that. And it kind of goes to, all right, well, here we go. We're going to do the same type of concept where we're going to look at the plane at t equals 78, but then we're also going to look at the plane at t equals 78 plus some value h. All right, so some later time. Technically, it could be an earlier time if h is negative, but that's kind of not necessary for this conversation. All right, so let me just draw my plane here, right, and then my plane here. And basically, we're going to start it off the same way, right? So watch what we do here. So we'll start by finding the average rate of change over the interval 78 to 78 plus h. And so, all right, what would that be? Now, I'll just kind of refresh your memory. Remember, x of t was 0.5 times t squared. So this will give you the distance along this runway. You plug a time value in, and the result is a meter value, how far down the runway it's gone. All right. So I'm going to kind of do this in the formula. So the change in distance would be the distance here, which I'd have to plug this time value in. So it'd be 0.5 times 78 plus h squared, whatever the heck that is, minus the earlier distance, which would be really 0.5 times 78 squared, which we did that before, is 3,042. The change in time would be 78 plus h minus the earlier time, 78. Now, if we simplified some of this, this is 0.5 times 78 plus h squared. I'm not going to do much with that. Minus 3,042. That we already did. And now here you see we just get h, which h, by the way, ends up being the length of the interval, right? So now this is a formula for the average rate of change over this interval here for this particular plane. And the question that we want is, well, we want the instantaneous rate of change, right? So we want the instantaneous rate of change. And now at the instant t equals 78. Notice the difference. Average rate of change over an interval, instantaneous rate of change is at an instant. So it turns out it's going to look a lot like this, but what did we say we had to do, right? We said if we keep making the interval smaller and smaller and smaller, right, we end up getting a better and better estimate for the instantaneous rate of change. So what do we have to do to the interval to get instantaneous rate of change? We have to drive the interval to what? Again, you can pause the video. Hopefully you said 0. So mathematically, how do I write that? How do I take this expression and say, all right, take that expression and drive the length of the interval to 0? Well, the length of the interval is h, right? It's from 78 to 78 plus h. That means the length of the interval is h. So we basically want to take the limit of this as h, if the length of the interval goes to 0. And you now have a formula, all right, that represents the instantaneous rate of change of the plane at the snapshot. If you were to take a little snapshot, a pic with your iPhone, as soon as it starts to take off and say, hey, here we go. In this picture, the time is 78 seconds. The plane is going this fast. Now, how do you actually do this? So how do we compute this limit? Again, if you have pre-calc last year, you know how to do it. If you did limits, if you didn't have pre-calc last year, we will show you how to do it. It's just a little bit of algebra. It's actually not too difficult, but we're not going to do that now. So hopefully that question got you all jacked up and excited to learn about limits this year. Take care.